All right, so that's your problem 51. All right. So problem 51 is a little bit lengthy and also a little bit like a little bit difficult. So this is just, but I think this is a good problem to illustrate several concepts that you have learned so far. So in this diagram, block 1 has mass, which is 460 grams, and block 2 has mass, which is 500 grams, and the pullet, which is mounted on the horizontal axle with negligible friction, has radius that's 5. The radius is 5 centimeters, and when released from rest, block 2. So this block 2 falls 75 centimeters in 5 seconds without the core slipping on the pullet, which means that the tension still remains the same. And what is the magnitude of the acceleration of the blocks? And what are the tensions, T2 and T1? And what is the magnitude of the pullet's angular acceleration? What is the rotational inertia? There's a lot of questions. So let's see. That's again. So in this diagram, it says that there's a tension T1 and there's a tension T2. Okay, and why are in previous problems we when you have two blocks and connected by a string, usually the tension is considered to be the same. But in this case, you found that it is not the same. Why is it not the same? It's because this thing can rotate. When this thing can rotate, then there's then the tension will be different. Okay, so that's why it can keep you rotating. All right, so. How do we approach this problem? You're asked to find, let's see, what are you asked to find? You're asked to find acceleration, tensions, 1 and 2, and the angular acceleration, and also rotational inertia. Okay, to calculate acceleration, then, this is basically, you use the equations of motion, so that should be easy. You have initial position that's defined that's to be initial at rest, so it is 0 here, and then after 5 seconds it moves down to 75 centimeters. So because it's below 0, so it is negative 0.75. So you can do that, or take this to be 0, or take this to be 0. Then if you take this to be 0, then this is positive 0.75. So either way, it doesn't matter. All right, and the whole thing is actually rotating this direction, which means that this block moves up and this block moves down. Okay, so that's it, because in order to keep the whole system, so they would they will be moving at the same acceleration, but the tension will be different. Okay, so now the equations of motion, the final position is equal to initial position plus initial velocity times time, and then plus 1/2 at squared. You have the time information, you have the displacement, so the final position is 0.75, initial position 0, no initial velocity, and then plus 1/2 acceleration, and then times time. Time is 5, and then you square it. So what is your acceleration? Your acceleration, after you do the calculation, you found out to be negative 0.06, okay? Negative 0.06 meter per second squared. What does that mean? It means that, on this block is moving down. So the acceleration here has a magnitude. We calculate it to be negative. That's because it's pointing downward. So the acceleration has a magnitude of 0.06. So I'm going to use the arrow to indicate the direction and just use the magnitude for the acceleration. So your acceleration has a magnitude of 0.06. That's going downward. Now, on the other hand, this M1 is moving from this point to that point, so the acceleration is upward. Okay, so it has a magnitude that's 0.06, also, but then direction is pointing upward. So now we just found out the acceleration, which is so your A magnitude is 0.06. Okay. What about the tension? So for tension, we can just draw the free body diagram. So for free body diagram, let's say this is your M1. Okay, you have tension that's going up, and then you have the gravitational force that's M1g that's going down, and the whole thing acceleration is going up. So you can use T1 minus M1g. That's your Newton's second law. The net force is equal to the mass times the acceleration. So you have your T1, that would just be M1a plus M1g. Remember, your your acceleration on block 1 is positive because it's moving upward. Okay, so you have the mass, which is 0.5, and then times 0.06, and then plus 0.5 times 9.8. So after you do the calculation, your T1, you should have your T1 that has a magnitude of 4.53 Newton. So we're going to keep that. So our T1 here is 4.53. We can do the same thing for T2. So for T2, let's draw a free body diagram. So for T2, I'm going to erase this. Oh, I'm going to erase this, okay? Because I already had the acceleration written down somewhere. So if we draw a free body diagram for T2, we have gravitational force, that's m2g, angular tension, again, that's pointing upward because it's away from the contact point. And the whole thing is moving downward. So you can use the m2g as a leading term. So you have your m2g minus tension, and that has to be equal to the net force. So you have your m2 and then times a. Now, because I define my coordinate to be positive downward, that's why I have the m2g as a leading term. It's, I kind of flip my axis. So your acceleration, the numerical value that you plug in, you should use 0.06, not the negative 0.06. Okay, so you have the m2, which is 0.46 times 9.8, and then minus your m2, 0.46 times your acceleration, 0.06, and the whole thing is your T2. So your T2 should have the value after you plug in a number, 4.87 Newton. Okay, so I'm going to write it here. So my T2 is 4.87 Newton. So we found our acceleration. We found T1 and T2, and then you also find the angular acceleration. So how do we find angular acceleration? If you have the acceleration, linear acceleration, that's 0.06, and that's on the tangent. So this is the direction of acceleration, and this is the direction of the acceleration. You have the linear acceleration. How is it related to the angular acceleration? If you recall, they are related by just the. I'm just going to write this. The acceleration, alpha. Alpha is equal to linear acceleration over the radius, okay? And the radius is given, so you have the acceleration, which is 0.06, and the radius is 5 centimeters, so it's 0.05. So after you do that, your alpha, you should have the value that's 1.2. That's radians per second. So that's easy, okay? Once you have the linear acceleration, then angular acceleration, they are related by this equation, okay? So the next one, so we calculate that. What is the rotational inertia? What is the rotational inertia of this one? We could have calculated this rotational inertia if mass of the disk is given, but the mass of the disk is not given, so you can't directly use the formula to calculate your rotational inertia. But there are other indirect way to calculate your rotational inertia, and that is, if you recall, I alpha, rotational inertia times the angular acceleration is equal to the net torque. Okay, so we can utilize this equation to find out what the I is, because we have the information of alpha. Alpha is 1.2. We just need to figure out what is the net torque. Okay, so based on this diagram, so I'm going to actually remove this to make it look cleaner. All right, so this is the central point. So radius, the radius is r, and it's pointing in this direction. So this is your r, and the tension at this point is pointing upward. Let's see, the tension at this point is pointing downward. Okay, because you have this object, so it's pointing downward. So right at this point, so it's pointing downward. So you have your T1. So by using right-hand rule, what is torque? Torque, so let's say this is torque 1. So torque 1 is equal to R cross F, right? So your R is the radius of the disk, and your F is your T1. And then what is and they are perpendicular to each other. But what is the direction, whether it's counterclockwise or clockwise? So you have R cross F. So you have R and then cross F. So your thumb gives you directions of the torque, which is positive because it's pointing outward. So I'm just going to use a dot to indicate that's pointing out of the whiteboard. Okay, so T1 is torque 1 is positive and has this magnitude of RT1, And so you have, we already have your T1, the radius stays the same, so you have this value. What about T2? The torque 2. So let's look at this diagram again. At this point, you have T2 that's pointing downward, and then the radius is pointing away from the center. So you have your R. This is direction of R, and this is direction of T2. So you use R cross F. So R cross F. So your thumb now pointing into the whiteboard. What does that mean? It means that it produces a negative torque. Okay, so your T2, if you use R cross F, that's equal to negative R and then T2. That's because it is pointing into the whiteboard. Okay, so what is our net torque now? So our net torque will just be torque 1 plus torque 2. So you have your RT1 minus RT2. And so your R is 0.05, and then times your T1, 4.53, and then minus your R, and then times T2, which is 4.87. So you can see that your torque, when you just look at this numerical value, your torque is negative. What does that mean? Your net torque is negative, which means that the whole thing is rotating clockwise. And that's consistent with our picture because the whole thing is actually rotating in this direction. Okay, so your net torque, you get a negative value, and I don't have the value here, but this whole thing should be equal to your I alpha, and your alpha should be in the same direction as the torque. So your alpha is 1.2, and then alpha is actually also negative as well because it's clockwise. So it's negative 1.2. So which means that your I value after you do a calculation is 0.014 kilograms times meter squared. Okay, so you can see that when you calculate net torque, it's just torque 1 plus torque 2. So after you do the calculation, you found that this value is negative. It just means that the rotation is clockwise. Clockwise is considered as negative rotation. So that the whole thing is equal to I alpha. I itself is a constant, does not change with the direction. But alpha comes with the direction. Now, when we calculate this, when we use this equation to calculate our alpha, we just calculate the numerical value, but we did not specify. We did not specify the direction yet. Okay. But then when you look at this, when you have the acceleration, when this whole thing is moving down, the acceleration is downward. So your alpha, and so the whole thing is rotating clockwise. So your alpha has to be negative as well. So just so it's consistent with the pictures right here. Okay. So that's basically problem 51. And then the next one I want to do is problem 56. All right, so let me draw a diagram again. So this. All right, problem 56. This diagram shows particles 1 and 2. Each, okay, I'm just drawing this as a particle. Okay, so each has attached to the end of a rigid massless rod of length, and this has 20 centimeters, and this has 80 centimeters. The rod is held horizontally on the fulcrum and then released. What are the magnitude of the initial accelerations of particle 1 and particle 2? Okay, so these two particles has the same mass, okay, but they are separated, and this is the point where they're going to balance, move up and down, about this axis. So, and the distance here, this is point 2 and this is point A. You also find the acceleration for each one, the linear acceleration. So how do we approach this problem? They have the same mass, and and it's going to rotate. So we know that you'll also find the linear acceleration. So there's a linear motion, and at the same time, it's going to rotate, which means that it has the angular acceleration as well. Okay, so that will be this will be the direction that we go for. So how do we do this problem? First of all, we probably need to know what is rotational inertia of this system, because the whole thing is rotating, right? So you have like so the diagram is actually this. So you have one object here and one object there, and it's on the thin rod. This thin rod has no mass, but this two particles has mass. And it's located at the separation that's 1 meters, but then this is your rotating axis. So this distance is 0.2, this distance is 0.8. So now we can just use the definition of rotational inertia to calculate what is the rotational inertia of this system. So rotational inertia of system would then be the contribution from this mass at one end and this mass on the other end, right? So you have the mass times L1 squared, and then plus the mass times L2 squared. This will be the rotational inertia when you have two objects placed on the distributed along the thin rod. Okay, so we have that, and then so I don't have the numerical value here, so it just said that you can just plug in numbers, no problem. Okay, now to calculate the linear acceleration, we have a rotational inertia. And so there's not much we can do about it. So I mean, what other information can we use? And we know that it's going to rotate. So there's, we can actually calculate. We can calculate the torque and utilize the equation that we just used, for previous problem. That is, I alpha is equal to the net torque, because we have the numerical value for our I, and then and you asked to find alpha. We just need to know what is the net torque. Now, if we look at this equation, look at this diagram, we have gravity. So you have the mg. This is your force. This is the force on this end. And then, what is the radius? This is the rotation axis. So the radius is this. So since this is vector, we can move this vector to here. So this is your R. So you can calculate. Let's say we call that torque 1. So torque 1 is equal to R cross F. So your R here is this. That's your 0.2. And your F is your mg. M is not given, but that's you'll find that it doesn't matter. And then sine of the 90 degrees, because they're perpendicular to each other. What about its sine, whether it's rotating clockwise or counterclockwise? R cross F, you can see that your thumb is pointing outward, which means that it is counterclockwise. So it is positive. So I'm going to use the dot to indicate that's positive. Okay? So you have torque 1 is 0.2 mg. We can do the same thing for this one. So at this end, you have your mg, and the radius is this, 0.8. And this is your R. So in that case, your torque 2 is R cross F. So your R is 0.8, and your F is mg. What about the direction? So R cross F, point your finger in the directions of first vector, and then sweep your finger toward the second vector. Your thumb gives you the directions of the torque, which is into the whiteboard. So in other words, the sign of torque is negative. So it's equal to negative, and it's pointing into the whiteboard. So what is the net torque now? The net torque will just be torque 1 plus torque 2. It has to be equal to I alpha. So your I alpha, you have the m, and then the 0.2 square plus 0.8 square, and then times alpha. The whole thing is equal to the summation of these two. So you have your 0.2, you have 0.2 mg, and then plus the negative 8 mg. So you can see that your m basically just get cancelled. It doesn't really matter. Okay? So what is your alpha? So your alpha, after you do the numerical calculation, your alpha is equal to negative 8.65 radians per second. So again, not negative. What does that mean? It's negative. If it's negative, it means that it's going to rotate in this direction, okay, in the clockwise direction. So that's why you got a negative, negative sign in front of it. But then this problem asks you to find the linear acceleration. How do you find the linear accelerations? Again, that's just by definition. Once you have the angular acceleration, then it becomes easy to calculate linear acceleration because your A on this one, your A1 is just equal to alpha times R1. And then alpha, if you just calculate the numerical value, so this would just be that. So you have your 8.65, and then times R1, which is 0.2. So your A1 should have the numerical value that is 1.73 meter per second squared. And for A2, you do the same thing. You have your alpha and you have your R2. So you have your 8.65 and then times 0.8. So you should have your acceleration that's 6.92 meter per second. Okay? So you can see that even though they have the same mass, but because they are placed at a different distance, to the in reference to the rotation axis, its linear acceleration will be different. And it's the whole thing going to rotate at the same angular acceleration, but the linear acceleration is different because your R here is different. The radius is different. Okay? So that is that.